Chapter 16 starts on page 413. We're going to be reviewing calculations revolving around IV medications. So just a review of some terms. So IV means intravenous, which in that case we are having a solution that is going directly into the veins. A continuous infusion is just what it sounds like. It's an infusion that is going to be given over time, just continuously dripping until that runs out. A piggyback is going to be a smaller volume IV bag that is going to be attached to the main line of an IV. So if you're following along in your book here on page 413, you can see we have a main IV bag here. And then this lady is hooking up what we call a piggyback, which is just a smaller volume IV bag, usually less than 250 mils. So she's just hooking that up to the main line of this IV here. And then to the left, we can see some IV tubing here. That's going to control how fast the solution is moving through the IV, as well as some tubing sets. Once again, you can also just do some different controls like drip rate, things like that on your IV set there. So I'll go back to my slides. So a solvent, I know we've talked about this a few times now. A solvent is the same thing as a diluent. So it's going to be diluting or dissolving the active ingredient. Usually your solvent does not have active ingredient in it itself. Now the solute is what is being dissolved by the solvent. So the solute is usually our active ingredient. A solvent and a solute combined together make what we call a solution. And then parenteral nutrition. So this is going to be nutrition that is given parenterally, usually through an IV. So usually we use parenteral nutrition for people who cannot eat by mouth or maybe are needing extra nutrients while they're in the hospital or in a long-term care facility or a hospice house, something like that. So we're going to start out today with looking at infusion rates. So just in general, it's important to know that a rate is just any value per unit of time. So for example, we think about speed when we're driving our car. Speed is a rate. We measure that in miles per hour, okay? So infusion rates are the same way. Infusion rates are just going to be an amount of fluid that's entering the body over a specific amount of time. So that amount could be expressed in volume per time, so like milliliters per minute or milliliters per hour, or it could also be expressed in how much of a drug is being received per minute or hour, like milligrams per minute or milligrams per hour. Or what we're going to focus on here in a little bit is what we call a drip rate or a drop rate, which is how many drops of the IV solution are they receiving per minute. So when we're calculating these rates, most of the time we're going to be looking for one of these things. Either the total volume that somebody is receiving with the order over a designated time, or how much medication they are getting in a specific time, like how many milligrams of active ingredient are they receiving in a specific time. That is important in case an order gets discontinued. Then we can easily calculate, how much medication has this patient already been given. We also need to calculate the volume to know how many bags we need to make up for the order. So, if it's a Friday and we're leaving, we won't be back until Monday, calculating the volume would let us know how many bags we need to prepare for the patient for their stay over the weekend. And then lastly, in some calculations, we'll need to know the length of time that an IV will last, so we know when the next bag will be due as well. Okay, so taking a look at the lecture worksheet here. Number 1 says, how much fluid will a patient receive in 12 hours at an infusion rate of 125 milliliters per hour? So let's look at the question here. They're asking for how much fluid. So we're looking at a unit of volume here, okay? The only thing we know about volume that's given is that they are receiving 125 milliliters in every 1 hour, okay? So we're going to be solving for how many milliliters will they receive in 12 hours. So we can solve these problems with ratio and proportion. So let's start with what we know. We know that in 1 hour, a patient will receive 125 milliliters. Now we can set that up equal to what we're looking for. We're looking for how much fluid, so we're looking for a volume. So I know my X will be on top, and I know that the infusion is lasting 12 hours, so my hours can go on the bottom here. Now we can solve with cross multiplication. So 125 times 12 gives us 1500. And then 1 times x is just x. So x equals 1500 milliliters here. So in 12 hours, they will receive 1500 milliliters. Now, number 2, what is the infusion rate in milliliters per hour of a 4-liter IV to run for 6 hours? So now this time we're looking for the rate. So our final answer should be in milliliters per hour. Well, we're given 4 liters here. So the first thing we should do is recognize that our answer needs to be in milliliters. We got to convert this 4 liters into milliliters. So 4 liters, 1 liter is 1,000 milliliters. So 4 liters would be 4,000 milliliters. Now we know that that is running for 6 hours. So once again, let's just start with what we know. We know that 4,000 milliliters is running for 6 hours. They want the rate in milliliters per hour or per 1 hour. So what we can do is just simply divide this to reduce it down. Or if it helps you out, we can set this equal to x over 1 hour. So we know that's milliliters per 1 hour. Either way, it's just going to be 4,000 divided by 6. So I plug that into my calculator, and x equals, I'm going to round to the nearest milliliter here. I got 667 milliliters. So my rate now would be 667 milliliters per hour. Okay. So now number 3, what is the infusion rate in milliliters per minute of a 3,000 milliliter IV to run for 4 hours? So I need to look at what I'm being asked. I want the rate in milliliters per minute. What I'm given is milliliters per hour. So I know that I need to convert my 4 hours into minutes. So we know that 1 hour is 60 minutes. So 4 hours, we can just take 60 times 4, which would give us 240 minutes. So now, once again, let's set this up with what we know. We know that 3,000 milliliters is running for 240 minutes. So now let's set that equal to how many milliliters are running per minute. So once again, you can simply just divide this, or if you like to set this up, x over 1 minute, it is still 3,000 divided by 240 gives us 12.5. So X equals 12.5 milliliters. So we know that my rate would be 12.5 milliliters per minute. Okay, now number 4 here. How long would a 1.5 liter IV last at 45 milliliters per hour? So here they're asking me how long or how much time would this IV last? So the only thing I know about time that's given is milliliters per hour. So I'm going to be solving for hours here. And I know that this is running at a rate of 45 milliliters per hour, but I see that they gave me the volume in liters. So immediately I need to recognize that I should convert this 1.5 liters into milliliters. So 1.5 liters is equal to 1,500 milliliters. Now we can start with what we know. I know my rate. There are 45 milliliters running per every 1 hour. So I can set that equal to what we're solving for. It's asking for how long or how many hours. So I know my X has to go on the bottom. And I know that my volume is 1,500 milliliters. Milliliter stays on top. So cross multiply here, we have 1,500, and we're going to take that divided by 45. So X here equals 33.33 hours. Now, if I am telling somebody I'll be there in 33.33 hours, they are not going to understand what that means. So I'm going to show you a trick to convert hours in a decimal into hours and minutes. So we know that our decimal, anything to the left of our decimal is a whole number, right? So we know that this is 33 whole hours. So 33 hours. So all I really need to do is convert this part of my number into minutes. And the shortcut to do that is just take this decimal and take that times 60 minutes, because we know that there are 60 minutes in every hour. So if I take 0.33 times 60 minutes in my calculator, it gives me 19.8, which is roughly 20 minutes, which makes sense because 33% is 1/3, right? So 1/3 of an hour is 20 minutes. So use this shortcut. It's very simple to convert from hours back into minutes. That makes a lot more sense, you know, telling somebody it will last 33 hours and 20 minutes rather than 33.3 hours. Okay, number 5. A physician orders heparin 1,500 units per liter for continuous infusion to run at 80 milliliters per hour. How many units will be delivered per hour? Okay, so let's just take a look at this first question before we go on to the next one. So this first question says, how many units will be delivered per hour? Now in this problem, I have two different rates here. I have units per liter and I have milliliters per hour. So we cannot just use ratio and proportion for these types of problems. We're going to have to go back and use dimensional analysis, which is multiplying fractions, okay? So anytime you see a problem that has more than one rate, let's start with dimensional analysis. So remember, we always need to start with what the question is asking for. Here, they're asking for how many units will be delivered per hour. So they're looking for units per hour. So step 1, start with what you're looking for, follow that up with an equal sign. Next step is to make your next fraction have this same numerator. So we want units on top. So if we look at what we're given here, this rate has units on top. So we're going to go with that one. We know that there are 1,500 units in every 1 liter. Now I'm going to look ahead here. I know that this rate is going to be in milliliters per hour. So what I would do is go ahead and transfer this liter into milliliters. So 1 liter is the same thing as 1,000 milliliters. So that's all I've done is just use this rate here, okay? So step 3, add a multiplication sign and then set up your next fraction so where the denominator of the first fraction is in the numerator of the second fraction. So I've already used this rate. The only one I have left is milliliters per hour. Milliliters is on top, so I'm going to take 80 milliliters here per 1 hour. Now when we do this, because these are diagonal, these units are actually going to cancel out, and we're going to be left with units over hour, units over hour. So that's what we are looking for. So now we can go ahead and solve. So remember, when you're multiplying fractions, you multiply straight across. So I'm going to take 1,500 times 80. That gives me 120,000. And then 1,000 times 1 is just 1,000. So now I can divide here. So 120,000 divided by 1,000 gives me 120. And my units here are units per hour. Now, the next question says, how many units will be delivered per minute? Well, sorry about that. I already have my units per hour, right? And we know that 1 hour is 60 minutes. So I could use ratio and proportion here. I know that there are 120 units running in 1 hour, which is the same thing as 60 minutes. They're asking for units per minute or per 1 minute. So you could simply just divide this here to reduce it down, or set it equal to x over 1 minute. It's just 120 divided by 60, which gives us 2. So x equals 2 units. So there are 2 units per minute. Sorry, I know that's small. It's kind of running together here. Make sure we separate those out from each other. So dimensional analysis, I know it's probably been a minute since you have done this concept, so really take the time to review the process of dimensional analysis. We'll go through a couple more examples here. Number 6, a 2-liter IV of D10NS contains 40 milliequivalents of KCl, which is potassium chloride. The IV was discontinued after 550 mils of fluid were given. How many milliequivalents did the patient receive? So here we're looking for how many milliequivalents. So let's see what we know here. We know we have a 2-liter IV of D10NS that contains 40 milliequivalents of potassium chloride. Well, that's important, right? We know that the bag contains 40 milliequivalents total. It was discontinued after 550 mils were given. Okay, so if we look here, we're looking for milliequivalents of potassium chloride. This question is not asking anything about dextrose or normal saline. So they're really just throwing this information in there to, get us sidetracked. So the first thing you should do on any problem, weed out any unnecessary information. So now we know that we're looking for milliequivalents of potassium chloride, okay? So we know that the IV has a total of 2 liters, and in that 2 liters, there are 40 milliequivalents of potassium chloride. We also know that the patient only received 550 mils of fluid. So the question's asking how many milliequivalents were in that 550 mils, okay? So let's start with what we know. We know that 2 liters has 40 milliequivalents of potassium chloride. Okay, so 2 liters is the same thing as 2,000 milliliters. And we know that there are 40 milliequivalents in that 2 liters. Now we can set this up equal to what we're looking for. We're looking for how many milliequivalents, so I know my X has to be on the bottom, did they receive? Well, they received 550 mils of the fluid. So ratio and proportion here, we can take 40 times 550. That gives me 22,000 equals 2,000x. So we're going to divide by 2,000, divide by 2,000 here. And that leaves me with 11. So x equals 11 milliequivalents of potassium chloride. So in some of these word problems, you're really going to have to read it a few times, throw out what you don't know, set what you do know equal to what you are looking for here. So now I would like you to go ahead and work on practice problems A in your book. Hopefully these first 6 examples can help you with that. If you're still struggling with this concept, please let me know and we can set up some time one-on-one to work together.